The last video made pole placement look relatively simple. The truth is the fact that most systems are not already in this convenient control canonical form. And while you could try to compute the eigenvalues of a general matrix, it becomes rather tedious and a little bit more difficult to see what's going on. And what we're gonna do is we're going to design a way to translate our system from some variables x into a new state space system given by states with z, where that system is in control canonical form. And one of the side benefits of that is that we're going to discover something kind of fundamental about control systems in state space form along the way. So if what we're doing is we're essentially designing this z, new state z, to be a linear combination of the existing states x. And what we want to make sure is that this matrix, the A matrix, there should be a z here, that matrix is in fact in control canonical form. So that's what I mean by this equation. And likewise, this new B matrix here, that new B matrix is in the control canonical form for the B matrix. And so it's a 1 followed by zeros. And so that's what we're going to try to impose in order to translate our system from any sort of state space representation into its control canonical realization. So this is our expression for the A matrix. So we're going to simplify this one step by just multiplying on the right by t. So that cancels that t inverse and puts a copy of t on the right-hand side. And so we're going to use this equation and we're going to use this equation to develop some rules for designing this transformation matrix T that's going to get us from a state space representation into a control canonical state space representation. And so we're going to do this first by using a 3x3 case, and that's going to help us build some intuition, and then we're going to argue that essentially the same thing holds for any bigger dimension system. So the way that I'm going to express this transformation matrix, it's a 3x3 matrix, and I'm going to write R1 to be the row vector that is the first row of the transformation matrix T. Similarly, R2 is the second row and R3 is the third row. So each of these vectors has 3 elements and it's a row vector. And so one of the things that you can see is that if I multiply T by A, so if T is in fact R1, R2, R3, and these are these row vectors, when I multiply by A, then what happens is that the first entry of the result, so this is my result, the first entry here, this comes from the first column of A and the first row of T. The second entry in the first row comes from the second row and, second column of A and the first row of T. And then the third element comes from the third column and the first row. And so what you're observing here is that this first row is made up of essentially the different columns of A multiplied by R1. And if we did that for the second row, you'd realize that it's the second row multiplied by the same 3 columns. So this is really just abstracting matrix multiplication out. And so one way to write that is simply that the first row of the result of T times A is just R1, the row vector R1 multiplied by all the columns of A, or just A. And then the same thing for the second row and the third row. And then if we take a look at the right-hand side of this equation that we started on the last slide, we'll just go ahead and write out what the control canonical form is for a 3x3 system. And so it means that we have these minus A1, minus A2, minus A3, and we have 1s right here. And then we're going to multiply by the T matrix again, which again is composed of these 3 row vectors. And so if we look at what the second and third rows are telling us, that's where the simplicity is. what we're going to observe is that this 1 is multiplied by this row. And so what that means is the fact that this second row right here is essentially telling us that R2 times A is equal to R1. Okay, so that's one identity. From the third row, we have that R3 times A is equal to R2. So that's another identity that we get out of the structure that control canonical form gives us. So we have that R3A is equal to R2, and now I'm going to do a little manipulation with these two to combine them together. So I'm going to substitute in when I see R, let's see, so when I see R2A here, I'm going to plug in what I have here. So I'm going to plug in R3A when I see R2. And so that gives me, this is R2 and this is A. And so that should be equal to R1 by this first equation here. So now what I've done is I've related row 2 to row 3, and I've also related row 1 to row 3. And so the handy thing about this is that if I know what row 3 is, then I can compute row 1 and row 2. All right, so we used one constraint, that is the control canonical form matrix, and now we have another constraint, which is the input matrix of the control canonical form. And so that means that T times B should look like 1, 0, 0. So again, by the same logic that we used to form this matrix here, we're going to get R1 times B, R2 times B, R3 times B, and that needs to look like 1, 0, 0. So that tells me that R1B is equal to 1, R2B is equal to 0, and R3B is equal to 0. That's just reading off these three lines here. So this is already in terms of R3. Now, since I have this identity that relates R3 and R2, I have the opportunity to stick it in here to simplify this into an expression that is also with respect to R3. So that gives me now, I replace R2 and gives me R3 times A times B is equal to 0. And then I use this next one that relates row 3 and row 1. I put that in here to translate R1 times B to R3A squared times B is equal to 1. So now what we have is we have three constraints on row 3. And this kind of makes sense because R3 is going to have 3 elements in it. So we have 3 unknowns. We need 3 different equations. And one thing we can do here is we can combine all of these equations together. We see that we have R3 on each, multiplying on the left for each of these. So if we extract R3, then we can write that R3 times B is equal to 0. R3 times AB is equal to 0. And R3 times A squared B is equal to 1. So this is just a way of aggregating all 3 of these equations, matrix equations, into a single one. And we're going to define this matrix as the special matrix, and I'm just going to call it the C matrix. C is for controllability, and we're going to get there in a second. And so what this is telling us, though, is that R3 times C is equal to this 0, 0, 1. So if I can do C inverse on both sides to get rid of this, I can figure out what R3 is. R3 is simply just this vector multiplied by the inverse of C. But for that to be true, C needs to be invertible. And that is going to be a property of A and B and AB together. And so if, in fact, we can do this inverse, then that allows us to compute R3. Multiplying R3 by A gives us R2, and multiplying R3 by A squared, or multiplying R2 by A gives us R1. So that, knowing R1, R2, and R3 would allow us to then give us this transformation T, which is the matrix that defines our new variable Z, in terms of our old state space state X. So doing this transformation, again, this is the 3x3 case, allows us to get from a state space model in X that is not necessarily in control canonical form into a model in Z, in the state Z, that is in control canonical form. And all of that is possible if this matrix C is invertible. So that means we can find an inverse. And so what we're going to do on the next slide is to generalize this for higher dimensions. So the top half of this slide is something that we already had from before. And so what we're going to claim is the fact that in general, the same procedure is true. If you have n states in one input, then you're going to form a controllability matrix that is just the extension of what we already did, which goes b, a squared b up to a to the n minus 1 times b. And if this is invertible, that allows us to compute the final row of our T matrix. And from that last row, we can compute all the other rows by multiplying by higher and higher powers of A, just like we did before. And the reason why we can do this is because nothing of the arguments that we laid out in the last slide, those all nicely generalize if n is equal to 4, n is equal to 5, and so that means that it just continues. And so using this methodology, this allows us to construct our new state space representation, which is in control canonical form, which allows us to then directly use our methods from pole placement. So just to be clear about the whole sequence then, is that if we are given a system that is not necessarily in control canonical form, then our first step is to transform to control canonical form. That involves constructing this controllability matrix, computing, if the C is invertible, computing the last row of our transformation matrix, and then using that to compute all the other rows of our transformation matrix. Once you have that, then you have your new system, which Z dot is equal to your new transformed A matrix, your new transformed B matrix, and so on. And so what you're going to be doing then is you're going to be finding your gain matrix in these new coordinates. So you're going to be finding the gain matrix K, and that's going to be in the Z coordinates. And so you're effectively going to be finding this K, what I'm calling this K sub C. Then in order to recover it for your original state space system, it's important to transform that K matrix, this KC, back into the K matrix that would be used on X. So you notice the feedback here is just, now you're just simply plugging in wherever you had Z before, this is going to be KC times TX. And so now our new controller matrix is simply just KC times T. And so this is the whole workflow in order to place poles and do pole placement for a system that's not in control canonical form. And so what you're noticing is that one of the key criteria for being able to do that is the fact that you need this matrix, this controllability matrix, to be invertible, or another way of saying that is to be full rank. And so that ends up being a very, very fundamental result in the state space analysis of linear dynamical systems. So specifically, this is an extension of what we already saw, is the fact that so we can only assign eigenvalues, so we can only do pole placement for arbitrary desired locations. So it means you can only do pole placement for any choice of poles if and only if this matrix is invertible or has full row rank. And so what ends up happening is if this is not full rank, then it is possible to place the poles in certain locations, but not in all locations. And so if you want to be guaranteed that any choice of poles is possible, then you need to have this controllability matrix criteria satisfied. And one of the very interesting things is that this has consequences in other aspects of control of state space systems, and that's something that we'll touch on later on in the class.